Right, this video is on the gas laws, and there are 4 that we'll be discussing in this video, and this is where we take gases from more of a conceptual discussion to a mathematical discussion. And so this is where the math really comes into play. And we see formulas and things like that. So we're going to be talking about how the variables of temperature, pressure, and volume relate to each other when we're talking about gases. So the first gas law, and these are named after people because these laws were discovered by people, so I guess it makes sense. The first one is called Boyle's law, and Boyle's law says this: the volume of a fixed mass of gas varies inversely with pressure at a constant temperature. So that's kind of wordy, so I want to talk about what that means. So first of all, there's a word in here that is the discussion of an inversely proportional relationship. And I'm not sure if we have discussed this or not. But yeah, we have in energy and frequency and wavelength and all of that. We've discussed it. So inversely proportional means that as one variable increases, the other one decreases. So in this case, this is a discussion of volume and pressure. And so we have an inversely proportional situation here. So as volume increases, pressure will decrease and vice versa. Okay, so that's what this law is saying. If we were to look at this graphically, and we looked at a graph of volume and pressure, an inversely proportional relationship will always look like a curve, because think about it. When pressure is small, so like this end, then volume is large. Okay, and that's inverse. And again, when pressure is big right out here, then the volume is small. So that's inversely proportional. All of these gas laws are going to be represented with a formula. And so the formula for Boyle's law looks like this. Okay, and so we read it as, P1 V1, or P1 times V1 is equal to P2 times V2. So this is a case where if you know the pressure and the volume of a gas in one instance, and maybe the pressure in another instance, you can find the volume. So we'll be manipulating these equations with algebra to always solve for the missing component. Another thing I want to show you about volume and pressure would be like if you had like a piston, a movable piston, and you had a gas. Okay, so think about it. If you were to take that same container and let's see, push that piston down. Okay, so what happens? Well, my volume decreased, and I'm going to even be more specific in my example here to say, let's say that my volume was divided in half, right? So my volume was divided by 2 when I pushed that piston halfway down into the container. Well, if my volume was divided by 2, it decreased. We should know that the pressure is going to increase, but inversely proportional means that it's going to increase by the same amount that the volume decreased. So in this case, if my volume decreased by half, my pressure is going to double. Okay, and so you will see questions like that pop up on my assignments and on the AP test, in terms of that it's not just as this gets bigger, this one gets smaller, but it can be much more specific if we know by how much one of those variables changed. So let's do a practice. And I'll show you how we can use this law. So the problem says a sample of oxygen has a volume of 150 milliliters when its pressure is 0.947 atmospheres. What will the volume of the gas be when the pressure is 0.8 or 0.987 atmospheres if the temperature remains constant? So I would suggest you do one of two things when you solve these problems. You can, as you read the problem, label your pieces of information. So like, let me change my color. So a sample of oxygen has a volume of 150. Okay, so that would be V1 because it's the first volume I encountered. Okay, and then keep reading, blah, 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 when its pressure is 0.947. Well, that's P1 because it matches with the volume. Okay, what will the volume of the gas be? Oh, V2 at a pressure of this. And now I have everything labeled. Okay, if you don't like that method because it's like kind of like junky in your problem, then I would recommend as you're reading it that down here in your space you're labeling, oh, V1 was 150 and then P1 was 0.947, V2 was question mark, and then P2 was 0.987. Now you don't have to do both of those because that's redundant, but I would recommend you do one of those. Either label it in your problem or jump down into your space and list your knowns and then the thing you're looking for. Because now all of a sudden I know I'm looking for V2. Okay, so I have this formula. Okay, and before I plug anything in, I will always solve for the variable that I'm looking for. You'll never see me do it the other way, and that's because it gets so messy and so junky. So I would highly recommend that you solve this thing for V2. So I need to get rid of P2, so I'll divide. So all of a sudden I have my, my problem, which gives me V2 equals P1, V1 over P2. And all I have to do now is plug in my numbers. So P1 was 0.947 atmospheres. P1 was 150 milliliters. And P2 was 0.98 atmospheres. Notice I'm putting my units in because notice what happens. My atmospheres cancel. I'm left with milliliters. That had better be the case if I'm looking for a volume. I punch this out on my calculator. I'm going to round to 3 sig figs because that's my fewest in my problem. And I end up with 144 milliliters as my answer. You can kind of justify that based on what we have learned, this inversely proportional relationship, because look, the pressure, right, increased by just a little bit, so we would expect the volume to decrease just a little bit. Oops, and it did. So sometimes I think it's important that you justify, like, yeah, that answer makes sense, because that's what I would expect to have happened. Okay, so that's Boyle's law. Deals with pressure and volume. All right, there's a second law called Charles's law, and this states that the, oops, still on my eraser. So the volume of a fixed amount of gas at constant pressure varies directly with the temperature in Kelvin. All right, so this time we're dealing with a directly proportional relationship, and we're dealing with volume, and we're dealing with temperature. Okay, so again, directly proportional is going to be as one increases, the other increases. So this time we're looking at as V increases, then T increases, or as V decreases, T decreases. It's directly proportional. A graph of a directly proportional relationship between volume and temperature will be a straight line with a positive slope, okay? And this also has a formula that looks like this. Okay, where T1 and T2 are in units of Kelvin. And if you don't remember, Kelvin is calculated by taking your Celsius temperature and adding 273 degrees. Okay, so that's very important. If you try to do a gas problem with degrees Celsius, you'll always get the wrong answer. So you're going to have to train your brain to start to change all of your temperatures to Kelvin. It's a huge deal. Okay, so let's just try a problem here. All right, at 0 degrees Celsius, the volume of a gas is 375 milliliters. To what temperature must the gas be heated to occupy a volume of 500? All right, so again, I don't care which way you do this, but I would identify what you have. So this is going to be my T1. I'm going to have to change it though, so we'll take care of that. Or you can do it right here. Well, that would be 273 Kelvin. Okay, the volume is 375. That's V1. To what temperature, T2, question mark, must the gas be heated to occupy? And here's V2. Okay, so again, I don't care how you do it. T2 was my unknown. V2 was 500. All right, so let's go for it. Okay, so I did this one on purpose because this is where our algebra skills sometimes will get us. I need to solve this thing for T2. I need T2 by itself, right? So right now I've got a couple problems. It's in the denominator, and I need to get it out of the denominator. There are several ways to do this, and you can solve it in whatever way is the easiest for you. You just can't break algebraic law. So probably the easiest way to do this is to cross multiply, because if you cross multiply here, you get rid of all your fractions, and then it's easy. So if you cross multiply, you'd get V1 times T2 equal to T1 times V2. And then it's very easy for me to get T2 by itself. I would divide by V1. And I end up with T2 equals T1 V2 over V1. Okay, so I'm going to leave that there so I can fill in my stuff. Now, I'll show you a second way. If you're doing it more of an algebraic approach, you're probably taught to, you got to get T2 off the bottom of this. So multiply both sides by T2, right? But then over here on this side, you have to get rid of V1 and T1. So you'd have to divide by V1, divide by V1, and multiply by T1. I mean, it's a mess, right? However, look, V2 T1 over V1, which is exactly what I had down here. So I'll just say to you that cross multiplying is probably the simplest way to do it. But however you want to algebraically solve this is up to you. Plug in my numbers and I'm good. Just watch your ones and twos, make sure they go in the right place. So T1, 273. V1, 375. And V2, 500. My milliliters cancel. It's going to leave me with Kelvin, which makes sense for a temperature. I'm going to go with my lowest number of sig figs, which would be 3. And I get 364 Kelvin. Again, we can kind of justify it. So watch, the volume increased. Okay. And so I would expect my, wait a minute. Oh, yeah. Okay. So the volume increased from 375 to 500. And so the temperature I would expect to also increase. And so I started at 273 and I ended up with 364. So that makes sense, and I should be able to rationalize that in my brain. So that's an example of Charles' law, which relates temperature and volume to each other. Okay, so moving on. There's a third gas law, which is called Gay-Lussac's law. And this one states that the pressure of a fixed mass of a gas at constant volume varies directly with temperature in Kelvin. Okay, so again, I've got a directly proportional relationship, and I'm talking about pressure, and I'm talking about temperature. So it's going to be very similar to the last law we just did. If it's a proportional relationship, this time I'm talking P and T. It's going to look like that straight line again. And my equation is going to look very similar to the one we just did. Right? Do you see how this and this are the same, except it's just switching it from V to P? Again, temperature must be in Kelvin. Okay? So you notice that these are kind of all the same, the problems. It's just learning how to manipulate these formulas and things like that. So let's try one. All right, so at 120 degrees Celsius, the pressure of a sample of N2 is 1.07 atm. What will the pressure be at 205 degrees Celsius, assuming the volume stays constant? All right, so T1, we need to change this, of course, to Kelvin. So 120 plus 273, that'd be 393. The pressure, here we go, so that's P1. What will the pressure be? So P2 equals question mark at 205 Celsius, so that must be T2, but I gotta add 273 to that, so that makes it 478. So this time I'm looking for P2. So this one's not quite as bad. I could cross multiply still if I wanted to, but I can actually do this simpler in one step by multiplying both sides by T2. Right, so I have P2 equals T2 times P1 over T1. And again, I just plug everything in, being careful that I put everything in the right spot. My kelvins canceled even with ATM, which is correct for a pressure. I do my math. I'm going to round to, three sig figs. And I got 1.30. So again, we should try to rationalize this. We know it should be a directly proportional relationship. So my temperature increased. Okay, so we would expect my pressure to also increase, and it did. So we can justify. Okay, and then there's one more law left, which is a little bit different, but it is called the combined gas law. And as you might guess from its name, it combines the other three laws together. So it expresses the relationship between V, T, and P for a fixed mass, meaning it's not changing, of a gas. All right, so this one looks a little bit different. And actually, this is pretty cool because it is the 3 laws combined, and I'll show you. Okay, so this is what the combined gas law looks like. Again, T must be in Kelvin. Okay, so let me show you how this is all 3 combined. So if we were to scroll back up and look at Boyle's law, Boyle was P and V, assuming that temperature was constant. Well, look what happens. If you say temperature is constant, then T1 equals T2, and they would just drop out. And look what law that is. That's Boyle's law. Okay, if we play this same game for the other 2 laws, we very well could. Charles' law is the relationship between volume and temperature, assuming pressure is constant. So if we assume pressure is constant, then P1 would drop out and P2 would drop out because they're equal to each other, and that's going to leave me with Charles' law. Okay, so it's kind of cool. The same thing for Gay-Lussac's law, which is it's pressure and temperature. So assuming volume is constant, so if that's the case, V1 would equal V2, and they would drop out, and there you have what we just learned was Gay-Lussac's law. So all 3 laws are hiding in the combined gas law if you know how to use it. So let's do a practice. Okay, the volume of a gas is 27.5 milliliters, V1 at 22 degrees Celsius, T1, although we need to change it, so 22 plus 273 is 295. And a pressure of this, P1. What will be the volume, V2, at 15 Celsius, T2, so 15 plus 273, 288, and a pressure of this, P2. All right, so V1, P1 over T1 equals V2, P2 over T2. And I'm looking for, what am I looking for? V2. So I need to get rid of P2 and T2. So to get rid of P2, I would divide both sides, right? To get rid of T2, I would multiply both sides. And so my new formula, V2 equals T2V1 P1. This is a mouthful for P2 T1. And again, if you have everything labeled, all you have to do is plug everything in where it goes, being careful not to mix your 1s and your 2s. So T2 is 288. V1 was 27.5. P1 0.974, P2 993, and T1 295. So my kelvins cancel, my atmospheres cancel, and it's going to leave me with milliliters, which I would hope would be the case because this is a volume. 3 sig figs, and if I crunch this correctly, comes up to be this. Now this one's a little harder to rationalize, and I'll tell you why, because it's all relationships combined. So like if you look at like what happened to temperature, well, the temperature went down, right? So temperature went down. So if it was just temperature, we would expect the volume to also go down, but we also have pressure. So pressure in this case went up. Pressure went up, so we would expect the volume to go down. Okay, so actually, so the volume would decrease in both scenarios, so we would expect my volume to be less than 27.5, and it is. So that one, again, wasn't as bad as I thought, but it's a little harder to justify. So those are your first 4 gas laws. They're